Hi students. So today morning we discussed about how to estimate a, qualitative dependent variable model, particularly its simplest form, the linear probability model or LPM. So the LPM can be estimated using OLS method, as we discussed earlier, ordinary least square method, which is very common. We are very familiar with that, and in all the previous 4 modules we have extensively used ordinary least square or some of its modified versions or extensions like weighted least square, generalized least square, two-stage least square, three-stage least square, etc. So all these methods basically broadly under the family of least square procedures. Then I told that the LPM model suffers from various drawbacks. One major drawback is the linear structure of probability. Basically, it assumes that as the explanatory variable increases, the change in probability of success or the change in probability of something happening also changes uniformly or linearly, which is unrealistic as we discussed. So there are certain models like logit model, probit model under the class of qualitative dependent variable models, which are more realistic, which basically assumes a non-linear pattern of probability. I explained with example that particularly if a household is very rich, then the with every unit increase in income, the change in probability, the increase in probability for buying house is very marginal. Similarly, the poor households, for them also the change in probability due to change in 1 unit of income for buying house is marginal. Whereas in the middle income group, for same 1 unit increase in income, the change in probability, increase in probability or improve in probability of buying house will be higher. So these non-linear patterns are captured by the probit models and logit model, and other drawbacks which we discussed about LPM model are also improved. But the difficulty is the logit model and probit model, they use maximum likelihood estimation procedure. So before I discuss probit model and logit model in our next video, I'll briefly introduce to you about the procedure of maximum likelihood estimation. So I'll just introduce it conceptually, I mean at a very basic level, and for understanding very basics of maximum likelihood estimation procedure, you can follow Ramanathan or Gujarati or even Pindai Gruvenfeld, which is which are references which we have been using for our course. So the preliminary understanding about maximum likelihood estimation procedure is given there, and I'll discuss that. Now, before I come to maximum likelihood estimation procedure, let us review the basic underlying idea about the least square procedure. So if you go back to one of our initial classes, we discussed that if you are observing, say, let us take up 2 variable model for easy explanation. So in a 2 variable model, let us take y is the dependent variable and x is the explanatory variable, and we have some observations on x and y for for some of the observations in our sample. Assume we have 10 observations like that, and if I put in a scatter plot in our in a graph where x-axis represents x variable and y-axis represents y variable, these small circles are different observations. We have 10 observations here. So in econometrics, what we are trying to do, we are trying to fit a curve in such a manner which is best fit, which best explains the movement of y for change in movement of x. Okay, That is what we are trying to explain in an econometric model, where y is the dependent variable, x is the exponential variable. And if I am using a very simple model, y is equal, say if it is a cross-section data, yi is equal to say a0 plus a1 xi plus ui. This is the standard model which we have been discussing for two variable model. So in OLS, what we try to do, we try to minimize the square of deviations of these observations of y. Okay, these are basically observation of xy. Okay, these are coordinates. This say for example, if it is observation number 7, this corresponds to x7 and y7. Okay, pair of x and y represented by this circle. So in least square procedure, we are trying to fit a curve such that the vertical distance between these points or these observations and the fitted line, okay, the square of the deviation, the square of the vertical distance between the actual observations and the fitted line, or corresponding point on the fitted line is minimum. Okay, so possibly there are many infinite possible lines can be drawn to represent all these points. In this example, we have two. Maybe there is one line x, there is one line y, I mean green, given in green, one in red, another is in green. And if I calculate the sum of square of deviations of these actual observations from the corresponding point from the green line and red line, then comparing between the two, for whichever line that sum of square is minimum, we'll be treating that as a better fit. Okay, so here say for example, the sum of squares of deviations for green line is 10, and sum of squares of deviations for the red line is 21. So 10 is lesser than 21, so it may suggest that the green line is a better fit compared to the red line. So if there are infinite possible lines are there, which we can use to explain the pattern of relationship between y and x. Basically the pattern suggests how y varies for variation in x. So this pattern can be explained by this pattern of based on these 10 observations can be explained by infinite straight lines, and out of that whichever line gives the sum of square of deviation to be minimum, we'll consider that to be the best. Then how to choose which one is minimum? For that, calculus made our life easy. We basically took the sum of square of deviation, which is maybe sum of di square, and that we tried to minimize by taking the first order partial derivative with respect to a0, a1, and then from that we got setting that equal to 0, setting the first order derivative, partial derivative, setting it equal to 0, then we derived the normal equations, and from that we got formula for a0 and a1. If you remember the formula for the intercept, that is a0 hat was y bar minus a1 hat x bar. Okay, y mean minus a1 hat, that is estimated value of a1, and x bar. Okay, and the formula for a1 hat was sum of small yi small xi, where small yi is deviation of y from its mean, and small xi is the deviation of xi from its mean. So your a1 hat was summation small y xy, sum of yi xi whole divided by sum of xi square. Basically, let me write down that formula. So basically the formula for my pen. The formula for a1 hat was equal to summation yi xi over summation xi square. So these are basically in lowercase yi, lowercase xi, and in the denominator summation xi square, where y small yi is capital yi minus y bar, and small xi is capital Xi minus x bar. Okay, so this was the formula for a1 hat, and for a0 hat, which is intercept, the formula was y bar minus a1 hat x bar. Okay, so using calculus, we found among infinite possible straight lines, we find out that particular line which minimizes the sum of square of deviations of actual points from the fitted line, and this procedure is popularly known as the least square procedure, or specifically ordinary least square procedure, or OLS. So in least square procedure, we are trying to minimize something. We are trying to minimize the sum of square of deviations. In maximum likelihood procedure, which we are going to discuss, we'll try to maximize the likelihood. Okay, so one is a minimization principle and another is a maximization principle. So before I take up the mathematics of maximum likelihood estimation procedure, there is a small example given in Ramu Ramanathan, which is in our reference. You please go through that. That basically, in a very simple way, tries to explain the concept of maximum likelihood procedure. It is using an example. It assumes that there is a drug manufacturing company, pharmaceutical company, which has manufactured a drug for a particular disease, and the company claims that the success rate, the probability of success of this drug is say 90%, or the probability is 0.9. Okay, so this is claim of the drug manufacturing company or the pharmaceutical company. Now there is a government agency, say the authorities of drug administration, which basically certifies the success rate of the drug. So perhaps as per this agency, the success rate of this drug, which is invented by the manufacturing company, I mean pharmaceutical company, is 0.7. Okay, so there is a dispute between them, right? So the pharmaceutical company claims the success rate of the drug which they have newly invented for a particular disease is 90%, or probability is 0.9, probability of success is 0.9, and the government agency which is certifying the success or the performance of the drug, they claim that the success rate is 70%, or probability of success is 0.7. So now when there is a dispute like this, how to resolve it? So if they come to a statistician or econometrician to resolve the dispute, what the econometrician or statistician can do, they can perhaps administer this drug to say a sample of patients. Assume there are they have picked up 10 patients suffering from the disease, and they have administered the newly invented drug, and they found 8 people got cured after administration of the drug. So for this econometrician, he found that in a sample, the success rate is 80%, or the probability of success is 0.8. Now, given that he found in the sample the success rate is 0.8, what is the probability that this sample is coming from a population where success rate is 90%? And what is the likelihood that this sample is coming from a population where success rate is 70%? How to establish that? Okay, so the econometrician is trying to, it's a binomial distribution, right? The probability of success is this, probability of failure is 1 minus that. So the econometrician basically will try to assess the likelihood of this drug coming from a population with a success rate of 90% versus the likelihood of the drug coming from a population with a success rate of 70%. So applying the appropriate formula, basically, which is NCR, probability of success to power what found for the sample, and so basically I can give this with this formula. So basically, if this sample belongs to a population with probability of success of 0.9, okay, the likelihood function will be 10C2 0.9 to power 8 multiplied by 0.1 to power 2. So this is basically probability of success if it is coming from this population, and this probability of failure work if it is coming from this population. Okay, so using this formula, the statistician can calculate that there is a, there is a likelihood of 0.19 that this sample is coming from a population whose success rate is 90%. Using similar formula, what is the likelihood that this sample is coming from a population where probability of success is 0.7? We can apply similarly 10C2 and 0.7 to power 8, 0.3 to power 2. So basically this 0.7 because P is 0.7 for this population, and obviously 1 minus P is 0.3, and using the similar formula you will find it that likelihood is, I think, 0.23. Okay, so here it is obvious that there is a higher likelihood that this sample has come from the population with success rate of 70%. Okay, because likelihood is 0.23 that the sample comes from the population with success rate of 70%, and the likelihood that this sample coming from a population with 0.9 or 90% success is 0.19. So 0.23 is higher than 0.19. So there is a higher likelihood that this sample has come from the population with success of 70%, success rate of 70%. Okay, so here we have just two possibilities, so it is easier to calculate. If there are n possibilities, infinite possibilities, then we can apply calculus, and the similar thing for the maximization principle. Maximum likelihood is basically maximization principle is applied, where the first order condition will be equal to, I mean, the first order partial derivative can be set equal to 0, and then the second order will be negative. Okay, so basically now you know, after explaining this basic idea of likelihood and higher likelihood or maximum likelihood, we can now go to the mathematics of it. So like our two variable econometric model which we had discussed earlier, let me assume we have a two variable model here where yi is equal to beta 1 plus beta 2 xi and ui plus ui. Okay, so this is my two variable model. So what are the knowns and unknowns here? Like as we discussed earlier, we have the data on yi, we have data on xi. So yi and xi are known. What is unknown? Unknown is beta 1, beta 0, beta 1, beta 2, and obviously the stochastic error terms, right? So as we did here, basically this particular line was represented by a particular intercept and particular slope. The red line is given by a different intercept and different slope. So there also we tried to search for different lines, that is different intercept and slope, which will characterize that line, and among that we found out the line which gave us minimum sum of square of deviations. Okay, so here we'll try to calculate maximum likelihood. Okay, so here we progress like this. We have y as known, x as known, and similar to earlier problem, we don't know the intercept, which is beta 1, we don't know the slope coefficient, which is beta 1, and of course the variance. Okay, so under these assumptions we can basically try to find out. Let us assume that y is normally distributed, so the dependent variable is normally distributed, so then ui also is normally distributed. So if yi is normally distributed, we can find their joint probability density function given by this formula. Okay, where y1, y2 up to yn, okay, these are known, and these are characterized by these parameters, which is this is basically the mean, right? The mean is beta 1 plus beta 2 x, and the variance is of course the sigma square. So given these unknowns, okay, we have the known values of y1, y2, yn, and let us formulate the joint probability density function with this formula. And if we assume that y1, y2, y3, etc., are independent from each other, then for each yi, we can have the probability, the probability density function as y1 for given beta 1, beta 2, beta 1 plus beta 2 x and sigma square. Similarly for y2 conditional upon that, for y3 conditional upon that. So if they're independently distributed, we can take as the product of each of the term. Okay, and then if for each y1, for each yi, that is y1, y2, y3, etc., assuming they are normally distributed, the normal distribution function, the probability distribution function will be given with this formula, that is the standard normal distribution formula. So if they are jointly their joint probability distribution function, which is basically product of each of the terms, can be given by this formula. So only difference here is, here it is here it was sigma, here it is sigma raised to the power n. Similarly root over 2 pi, again raised to the power n. So when we are taking the joint probability density function, so then these terms are raised to the power n. So now this one is a likelihood function. Okay, this one is the likelihood function, which I can rewrite this way. This likelihood function is defined by a particular value of beta 1, particular value of beta 2, and particular value of sigma square. Okay, so for a particular set of value of beta 1, beta 2, and sigma square, we have the likelihood function for basically for the joint distribution function of yi, y2, etc., for given parameters or these unknown parameters, which are sigma 1, sigma 2, beta 1, beta 2, and sigma, etc., sigma square, etc. So now, like this, there are n possibilities. For basically n set of values of beta 1, beta 2, and sigma square, you have n likelihood functions. Okay, now among these n likelihood functions, we are trying to find that particular value of beta 1, that particular value of beta 2, and that particular value of sigma square, that set which maximizes the value, which maximizes that likelihood. Okay, so for that, in the least square procedure, we can apply the calculus, where basically this is the likelihood function, and here the unknown parameters are beta 1, beta 2, sigma square. So we are taking the partial derivative of that likelihood function with respect to beta 1, beta 2, beta 3, and setting that equal to 0, and then solving this equation. Will find similar formulas as we found in the least square procedure, and then after solving these simultaneous equations, we can get the values of beta 1, beta 2, and sigma square, which in a best possible way gives us the estimates which maximize these possibilities that this sample has come from a particular population. So again, I'm basically trying to I'll summarize the ideas. Basically, when you estimate a particular equation, we estimate that equation drawing data from a particular sample. Okay, now we are trying to find out this what is the best likelihood, that what is the best possibilities that this particular sample has come from a particular population. Okay, so this is done by estimating the likelihood function, that what is the likelihood that this sample has come from population 1, what is the likelihood that this sample has come from population 2, from population 3, like that, etc. And among all likelihood, we estimate what is the maximum likelihood. Okay, and depending, based on this maximum likelihood, we then determine that this sample has come from a particular population. So accordingly, we indirectly derive what is the value of beta 1, what is the value of beta 2, what is the value of sigma square, and these parameters basically characterize that particular population which we think, from which the sample is drawn. Okay, so there are many interesting, there is one difference. If you observe the formula for the variance. Okay, so here the formula for variance or the maximum likelihood estimator is 1 over 1 over n, then sum of ui square. In OLS, it was 1 over n minus k. So here it is 1 minus n, there it was 1 minus k. And this maximum likelihood estimators have many interesting properties. Of course, when UI is distributed normally, then the maximum likelihood estimator and the OLS are identical. Okay. And the interesting properties of maximum likelihood estimators are they are consistent. So when the sample size, they are asymptotically unbiased. When the sample size increases, then the the maximum likelihood estimate on an average will give the population parameter, and they are asymptotically efficient. So if the sample size is very large, there is no other estimator which will give lesser variance. Okay, so this is with the least variance, so it is asymptotically efficient and asymptotically normally distributed. So basically my attempt here was to give you very basic idea about the maximum likelihood estimators estimation technique. So as I said, you can refer the book like Ramu Ramanathan, Gujarati, etc. for having very basic understanding about that. And in the next lectures, we will discuss how to apply this maximum likelihood estimation techniques and use probit model, logit model for estimating qualitative dependent variable models. Okay, thank you.